Oh, you're already there. Let me grab a seat. This video is about my latest publication in BioEssays. It's called Alternating Terminal Electron Acceptors at the Basis of Symbiogenesis, How Oxygen Ignited Eukaryotic Evolution. And before I can give you an idea what this publication is about, I have to introduce you to another publication which it responds to, and that's a revolutionary paper by Martin and Müller in 1998 in the journal Nature, which was called The Hydrogen Hypothesis for the First Eukaryote. So what's so revolutionary about that paper? It's a paper that states that actually the complex, large eukaryotes evolved from a combination of an archaea and a bacterium. And these two simple prokaryotes lived together in symbiosis. Then the archaea took up the alpha proteobacterium, which was destined to become the mitochondrion. And this living together gave rise to all the adaptations that we now find in the eukaryotes. So that's really a revolutionary concept. And not only a revolutionary concept, but more importantly, the concept that I think is correct. Okay, so what was the specific incarnation that they chose? They said that the symbiosis between the archaeon and the bacterium was based on hydrogen, the hydrogen hypothesis for the first eukaryote. Why did they think so? Because you can find hydrogenosomes, so organelles that generate hydrogen, because hydrogen is used as the final electron acceptor all over the eukaryotic tree, especially with parasites and in anoxic environments, so environments without oxygen. This hydrogen that's then produced by the bacterium is used by the archaea, which is a methanogen, to give off the electrons to carbon and then generate methane. Okay. So the concept is revolutionary, is correct, but is the specific incarnation, so the basis for the symbiosis, correct as well? And here I have some problems. Why do I have problems with this specific model? Because if you look at the development of the eukaryotes, they appear rather late in evolution, as is shown in this picture, after the GOE, so after rises in oxygen levels on the planet Earth. This rise in oxygen would lead to a problem, because electron transport chain acceptors, for instance the case that's used for the genesis of methane, are very, very sensitive to even low level of oxygen. So they are inhibited or even destroyed by oxygen. And also hydrogen facilitation or hydrogen production is inhibited by oxygen. So that doesn't seem to make sense, because the eukaryotes, of course, had their great advantage in using oxygen as the final acceptor. And the alpha proteobacterium has a normal electron transport chain ending with cytochrome C oxidase that makes water from oxygen by using the electrons coming from cytochrome C in the electron transport chain. So that already gives you the idea, hey, could that really be true? And secondly, it doesn't reflect in any way what we find in modern day eukaryotes. What do we find in modern day eukaryotes? In modern day eukaryotes we see that, you could say, the host, the cytoplasm, ferments. It generates ATP, for instance, from glycolysis, using glucose as a starting point, and making end products like lactate or pyruvate and the electrons in the form of NADH, and leaves it to the mitochondrion, for instance, to take care of this. So we see that actually then the mitochondrion is the wastebasket of the cytoplasm. And that's actually the basis of my theory. Probably the symbiosis in the beginning was due to the fact that you have a lot of environments with small but strong gradients in oxygen levels. On the one hand you have the bacterium, which can use oxygen. On the other hand, there is an alternative electron transport chain in an other archaea, doesn't have to be a methanogen, and this uses another electron acceptor, but this one is clearly oxygen sensitive. What would happen in a symbiosis? Only one of the two electron transport chains will work. Either our one, the one that's still in our mitochondria using oxygen, or the other one if there's not enough oxygen around. If there's enough oxygen, then this electron transport chain would be temporarily inhibited. And now we can see, as shown in this figure 2, how this could work out. You just leave your waste with the other organism that's still able to use its final electron acceptor, and the other way around. But then in the end, oxygen of course wins out, the electron transport chain of the archaea is gone, it's really destroyed by high levels of oxygen. There is no membrane potential anymore, and this cell can now take up the alpha proteobacterium, which leads to the mitochondrion, ROS formation, and all kinds of adaptations that bring us the eukaryotes as we find them today. I hope that I've convinced you that this is the way it all started out. Just have a look at our figure again. If you think it's too complicated, then just read the article, or you can also read all of the publications listed at the end of this video. I think it's less work to read my article, and I hope you enjoy it.